anymore, right? So let's see the distinction, okay? If you have a bond, like let's say H2O, you have a molecule, there's your Lewis structure, right? Now the OH bond, this is what we call an intramolecular force. Okay, intra means within, right? So a force that's within the molecule. So covalent bonds are actually broadly classified as intramolecular forces. Okay. Now we have the other one. It's called intermolecular force. So what's the difference? Inter means between the molecules. So how do water molecules stay together in the liquid phase, right? If you see water, a water bottle, that's a whole bunch of water molecules. And water, how are they held together, right? How are the water molecules held together so that they're not flying into the gas phase? That's held by what's called the intermolecular force. Okay, so remember that water is polar, and this is delta minus because the oxygen's more electronegative. H is delta positive, right? So there is going to be an electrostatic interaction between the positive end of water and the negative end of the neighboring water. Opposites attract, right? And so the water molecules are actually attracted to each other. And that's why they are held together in the liquid phase. Otherwise, water would be in the gas phase at room temperature, and that'd be detrimental to us, right? We need it to be in the liquid phase. So that force right there, that's holding all the water molecules together, that's what we call the intermolecular force. Okay, inter, which means between. So the forces between the molecules is what we're going to be concentrating on this chapter, right? Whereas in the entire semester, we've really been just talking about bonding, right? Which is the intramolecular force, okay? So that's our little segue. So intermolecular forces, you're going to see are going to be dependent on whether a molecule is polar or not. And if we know the polarity, we can actually, predict what type of intermolecular forces, and then that also means we would know about boiling points and melting points. So pretty cool stuff. So let's get to it. All right, so before we get into all the intermolecular forces, we will review the states of matter, right? Remember, we have solid, liquid, gas. I'm going to go through and just quickly review those real quick, right? Look at this table. We've seen this before, right? So the states of matters differ by basically the kinetic energy, right? Solid has the least kinetic energy. Gas has the most, right? And it's kinetic energy that basically governs how far the molecules are from each other. So the further they are from each other, the more, right, towards the gas phase that they are. So in solid state, you have molecules smashed right against each other, right? So it's very rigid, it's very solid, right? You can't put your hand through a solid, right? Because there's no space in order for you to do it. So it is about spacing, right? Then you add it a little bit of kinetic energy, right? You warm that solid up, and eventually the molecules can vibrate more, and then it starts to actually roll around each other. Okay, so that's what flow is. That's what why a liquid can flow. Okay, so more kinetic energy, right? And slightly a little bit more space in between them. That's why they can flow past each other. Then you keep adding energy, then what happens? They vibrate even harder, and then eventually they're completely free. They're not touching their neighbors anymore, and that's what steam is, right? That's what gas is. So that's the three states of water, right? So you got solid, which is we call ice. It's really weird that we call water three different things, or H2O three different things, right? We don't have terms like that for anything else except for H2O. Obviously, that's how important it is to us, right? So we call solid H2O ice, we call liquid H2O water, and we call gaseous H2O steam, right? But thank goodness we don't do that for anything else, because that'd be a problem memorizing all those, right? So what are the properties then of the three states, right? Remember that the solid is very rigid and it has a fixed volume and fixed shape. Liquid has a fixed volume, but it can take any shape of the container. And then if you have gas, that means that it is, no fixed volume and no fixed shape either. So what does it mean about the intermolecular forces for each state of matter? Well, think about it. If you're in the solid state, that means the intermolecular forces have to be really strong, right? Because what does it take to go from a solid to a liquid to a gas? It takes energy, right? So, um, for a solid to go to a gas, right, you would have to input a lot of energy, okay? And so therefore, a solid must have really strong IMFs, right? Because remember, right, like on the board that we did, the water molecules are held together by that IMF, by that intermolecular force. So in order for it to go into the gas phase, you have to break the IMF, right? You have to break that force. So you have to input energy, okay, for the two water molecules to completely separate, okay? So the stronger the IMF, the more likely it's going to be in, either the solid or the liquid state. Right? So liquid, of course, would have moderate IMF strength, and then the gas state would have the weakest IMF strength, right? Because it doesn't take that much to get it into the gas phase to completely break the IMF, right? Okay, so liquids, right? Here's a picture of it. Um, Notice it's not as jam-packed tight as like a solid. It is touching, right? The molecules are touching each other, but they do have enough kinetic energy to just kind of like go like that, and then also then move past each other, and flow past each other, right? But they don't have enough kinetic energy to completely be free of the IMF, right? Meaning breaking the IMF completely to become a gas, right? So when you're thinking about in terms of intermolecular forces, actually quite easy. You have really strong in the solid state, and that's why it's so rigid, right? It's like a glue that holds, think of IMS as like a glue that holds the molecules together. So the stronger it is, the more energy it's going to take for this, for the molecules to start doing this. So when you're going from solid to liquid, I think of it as you're loosening the IMF, right? You're not breaking the IMF completely, but you have enough energy just to loosen the glue a little bit. And so things can start to move around, okay? But to get to the gas phase, liquid to the gas phase, you have to completely, right, destroy the IMF. Pretty much, right? I mean, some gas molecules, right, they have a little bit of attraction too. So it's not completely zero IMF, but basically, it's gone because they're flying around, right? They're not even close to each other, right? So, you want to start to think in terms of IMF in that way, just as a glue. And as soon as you start doing that, you can really start to predict what are the states of matter based on, how strong you think the IMFs are, right? What if the IMF is strong, you're like, well, this compound's probably going to be a solid or a liquid, right? That has super weak IMF, like, okay, that compound's going to be a gas. And therefore, you also have an idea of the boiling points and the melting points, right? So if something's really weak, then it's going to have a low boiling point, right? So it's not going to take that much energy for it to go into boiling, right? And so on. So really, that's what this chapter is about, right? It's great. People love it because there's not a lot of math. You're not really calculating much. It's all qualitative assessment of the IMFs, right? Okay, so gases, right? They are weak IMFs. Okay, you can see that because the gas particles are far apart from each other, so the IMF's pretty much completely broken there. So that makes a gas really highly compressible, right? And expandable too. It can compress and it can also expand. Right? That's why it has no fixed shape and no fixed volume, right? Okay, and then the solids. We have the two types of solids. You have both types of solid. You have minimal space in between the molecules, right? So they're really jam-packed together. But if you have long range ordering, really ordered structure, we call that a crystalline solid. But if you don't have long range ordering, we call that an amorphous solid. Okay, so its crystal structure could look something like this. So you notice this picture looks a lot less orderly than this one, right? So a crystalline solid we love because they're really shiny, okay? And they're shiny due to the very orderly geometric pattern. What that allows is for light to hit it and reflect at the same angles everywhere. And you guys know about light now. These light waves, if they are interfering face to face, then it will give brilliance, right? In face to in face. Uh, uh, then you'll get addition, right, of the amplitude. And so you see brighter, right? And so that's why orderly structures like crystalline solids look really shiny to us, right? Because it's all these light that is reflected back is doing constructive interference, right? Now, the amorphous solids, we call it so because they look really dull, right? There's no long range ordering, and so therefore the light that gets reflected back is all over the place, and so they cancel each other, right? A lot of it cancel each other, so you don't get that brilliance, right? So crystalline solids, we value those. And you've seen them, like diamonds, like the one that we value the most, right? Diamonds really, really shiny, but even like table salt, right? If you look at table salt, like one little cube of it, you'll see that it really has long range ordering and it's shiny as well, right? Then your amorphous solids be like your plastic and your glass, not very shiny, right? Very dull, boring, right? Okay. Okay, let's review phase changes. We know this. It has to do with kinetic energy, right? So to increase the kinetic energy would allow you to go from solid, liquid to gas, right? But you can also, so that's adding heat, right? Adding heat is what can change phases, but you can also change phases by playing with the pressure, right? And that's easy to think about too. Let's think about a gas, right? Which is highly compressible, right? Because it has a lot of space in between the particles. So that means if you apply pressure, so if you increase pressure, what do? You squish the gas molecules together, and eventually you can squish it down to a liquid because now it's touching, right? And if you keep compressing, so if you keep increasing the pressure on a liquid, eventually you will turn it into a solid, right? And that's actually how diamonds are made, right? Under really, really high pressure, just carbon atoms, right? Under super high pressure forms diamonds. Okay. All right, so there you got the two things that the two factors that can change phase, right? Heat and pressure, right? So to go from solid, liquid to gas, you can add heat or you can reduce pressure, right? You want to go from gas back to liquid, back to solid, then you need to cool or increase the pressure. Okay. So now let's go to intermolecular forces. Okay. So we're going to learn all the different types. That way we're going to be able to kind of predict why things are, what compounds are solid, liquid, or gas, right? AKA boiling points and melting points. All right, so intermolecular forces is the force that holds the molecules together, right? Inter means between, molecular, and then forces. So between molecule forces, right? So all molecules are attracted to each other in some way, right? Now the attraction strength is going to be different, but there's always some sort of attraction, right? Because there's nucleus and electrons, right? We know that. Um, uh, Between two molecules, right? They both have positive and negative charges, right? So there is going to be some attraction. It's just how much, right? What is the strength of that attractive force or the strength of the IMF? And the strength of the IMF is what determines your state of matter. Again, right? Very strong IMFs, you get solids. Moderate IMFs, you have liquids. And then weak IMFs, things will be a gas at room temperature. Okay. So you can kind of, I mean, right now you already know things, right? You know molecules that are either liquid, gas, or solid at room temperature. So we can compare two compounds really easily. Let's compare CO2. Now I'm going to draw the structure of that versus water. water. Okay. This is a gas at room temperature. At room temperature, we know water is a liquid. And so now we actually can say, oh, why is it that water is a liquid and CO2 is a gas at room temperature? It must mean that the IMF of water is stronger than the IMF of CO2, right? Now we can just say that, right? So we will learn in a second here that the reason is because CO2 is non-polar. You see it? We've done this assessment before, right? To draw the bond polarity arrows, okay? And they cancel, right? So this is no net polarity. It's non-polar. Water here is polar. Okay. And we're going to learn in a second why polar things are stronger than non-polar things as far as their IMFs. Okay. And so that's why, even though water, which is 18 grams per mole versus carbon dioxide is 44.01 grams per mole, even though this is smaller, okay, it's a liquid in the liquid state, okay, as opposed to CO2. Okay, so let's talk about why molecules are attracted to each other. Remember when we did water earlier? We said water is polar and it has a delta negative end, which is the oxygen end, and then a delta positive end, right? And how the water molecules link together is the delta negative end will attract the delta positive end of the other molecule. So that's what it's about. It's just opposites attract. We call that electrostatic interactions. That's it, right? And remember Coulomb's law, right? Things that are oppositely charged, they want to be closer together. That's what stabilizes them, right? You lower potential energy by putting opposite charges closer to each other, okay? And then if you remember Coulomb's law, which was Q1 times Q2 divided by R, right? If you have larger charges, the stabilization is even greater, right? Remember, if it's 1 minus and 1 plus attracting each other, then 1 plus 1 minus multiplied together is 1 minus. So you have a 1 minus stabilization. But if you double that, now you have a 2 plus and 2 minus charge. Multiply that. 2 plus 2 minus is 4 minus. So you basically, by doubling the charge, you stabilize by 4 times, right? So you lower the potential energy by 4 times. Okay. So obviously the larger the charge, the stronger the attraction is going to be. And then the longer the distance, the weaker the attraction is going to be. Okay. Okay, so let's look at all of the kinds of attractive forces that we have, and we call these different IMFs. The main ones that we're going to go through: dispersion forces, dipole-dipole attractions, or dipole-dipole forces, and then we have hydrogen bonds. Okay. So we're going to go through and explain to you guys the source of attraction for each of these IMFs, and then also state what the strengths are relative to each other, and then the examples of different molecules that have these IMFs. Okay, so we're going to do dispersion forces first. What we're doing is we're going from weakest IMF to strongest, okay? So the weakest IMF is called dispersion forces. And dispersion forces are weak because you don't have dipoles. These forces are present in all molecules, but for nonpolar molecules, it's the only force that has it's the only force that nonpolar molecule has. And so that's why, people often associate dispersion forces with nonpolar molecules. Okay, so let's explain what dispersion forces are using the helium atom, okay? So everybody look at your periodic table, right? Helium, 2 protons, right? And 2 electrons. So you got the 2 protons here in red. Okay, the gray ones are neutrons. You don't have to worry about that. But there's your 2 protons and there's your 2 electrons. Okay. you can see that frame 1, 2, 3 are just three different snapshots of helium at different times. You can see that the electrons are in different places, right? Because they're always moving. So in frame 1, they're more or less balanced, as in there's one electron on this side and there's no electron on over there, okay? So you don't have an induced dipole yet, okay? Then in frame 2, same thing, right? You don't have, it's evenly spread out. You have electron here, you have an electron here, okay? But in frame 3, what happens is both of the electrons are on the left side now. That means that the left side of this atom is actually delta negative, and the right side is delta positive, but just momentarily, right? Remember, these are quick snapshots, okay? So this is what we call an induced dipole. It's induced by just randomly moving electrons, right? It's happenstance. And that's also why it's weak, right? So this dipole is existing in one instant, but in the next instant, it could be completely destroyed, right? However, in that instance that it has a dipole, it can induce a dipole in its neighbor. So there's that first helium, right? With a delta minus on the left side and a delta positive on the right side. When it sees a neighboring helium, it'll induce a dipole there, because now the delta positive side of the first helium atom will draw electrons to it, making the second helium atom also delta minus on the left side and delta positive on the right side. Then the second helium atom can do it in turn to the third, right? So each atom induces a dipole in the next. However, remember, these are not permanent dipoles, they're momentary dipoles. So in the next instant, it's gone, right? And so that's why dispersion forces are, well, they're unreliable, right? They're there sometimes, they're there, not there at other times. So they're unreliable, and that's why dispersion forces are the weakest of the IMFs. Okay. So just because they're weak, it doesn't mean that, they can't add up to be really strong. So that's what happens is if you find dispersion forces, you can find nonpolar molecules that are in the liquid state or even in the solid state. And that's because the dispersion forces can add up, okay, over a long chain, okay, over a long distance, it can add up and then it can be very strong, okay? So that's why when you're comparing forces, you have to compare the similar molar masses, right? Because the larger the molar mass, the larger the dispersion force, right? So to be fair, you have to compare molecules of similar molar masses. Okay, so the larger the molar mass, the larger the atom or molecule as well. So what that means is you have more electrons and you're going to have a larger electron cloud. And remember how it goes. If you have a very large electron cloud, the peripheral or the outermost electron, right, the valence electrons, are not held on as tightly by the nucleus. So they get pushed around a lot more easily, right? So that, let's say, when this atom bumps into the next, right? If this atom, if these were not helium, and let's say they're xenon, right? So they're much larger, then the first one can influence the next one a lot more easily because the electron cloud is so far away from the nucleus, okay? And so there's a term for this. This term is called the polarizability of the electrons. How easily these electrons can get pushed around and influenced, okay? So the larger the electron cloud, the more you have electron polarizability, and so therefore the stronger the attraction. That's why larger molar mass compounds will have stronger dispersion forces, because it's easier to induce a dipole in larger molecules. Makes sense, right? So that's size, one thing, right? The shape of the molecule also plays a part in the dispersion forces, the strength of the dispersion forces. Obviously, in order to get polarizability, right, to induce a dipole, the molecules have to come in contact with each other. Okay, so the shape of the molecule is going to determine how much surface-to-surface contact they can have with each other. So the more surface-surface contact, the larger the induced dipole, and therefore the stronger the attraction. Okay. Um, okay, so let's look at the size factor first. So here we have a table. We're comparing the noble gases, right? From helium down to xenon. Molar mass are right here. We know that as we go down a group, we're going to have an increase in size, right? Atoms get larger, and certainly more electrons and protons, and so the molar mass also gets bigger, okay? And what do you see for the trend of the boiling point in Kelvin? It also increases, okay? So again, as the size increases, the dispersion forces will get stronger, and stronger IMS means what? Higher boiling points, right? Okay, now let's look at shape. And here we have a fair comparison. The left molecule is N-pentane, the right molecule is called neopentane. It's a fair comparison because they're exactly the same molar mass. Verify for yourself. The left one has a chemical formula of C5, right? 1, 2, 3, 4, 5, and 6, 6, 12, C5H12, right? 12 hydrogen. On the right, 1, 2, 3, 4, 5, also 5 carbons, and 3 times 4, 12 hydrogens. Exactly the same molar mass, okay? But N-pentane is a rod-like molecule, right? It's a long molecule, like a rod. So they can form, right? N-pentane can form more surface-to-surface contact than neopentane. Neopentane is shaped like a ball. Now, two balls, right? They don't have very much surface-to-surface contact, right? So from just looking at the structure, and now you guys know all this, right? This is the beauty of it. You know how to draw the Lewis structure. You also know shapes, right? So you know what these are, largely shaped like. So this is ball, this is rod. Now you can predict which one's going to have the higher boiling point. So what do you think? You should say N-pentane has the higher boiling point because it has a larger area, surface-to-surface contact, and therefore will induce a dipole more easily than in neopentane, right? So the IMF, the dispersion force, they both have dispersion, right? Because they're both nonpolar, as you can see, CC and CH, right? They're both nonpolar, so both dispersion forces, but N-pentane is going to have much stronger dispersion force than neopentane. So therefore, N-pentane will have a higher boiling point than neopentane. Okay. You can see it here on this table as well. We have this graph. I mean, this graph has y-axis as the boiling point in Celsius, and then x-axis as the molar mass in grams per mole. We're comparing 5 different rod-like molecules here. Okay, so shape is the same, right? But what's different is the molar mass. So you can see that it steadily rises as the boiling point steadily rises as the molar mass rises, right? Well, again, why? Well, you have increased polarizability, right? And also more surface-to-surface contact because non-named C9H20 is a lot longer than, say, pentane is, which is only 5 carbons long. Okay. So the result of this is, I don't know if you guys have ever heard of hexane or pentane. You can actually buy hexanes at hardware store, I believe. The hexanes are liquids, right? Hexanes and pentanes are liquid at room temperature. Once you get up here to 14, 15 carbons, things start to become a solid, right? Which is remarkable because these are nonpolar molecules, right? Nonpolar molecules tend to be gases at room temperature, like CO2, okay? But CO2 has a what molar mass? About 44, so it's down here, right? And so that's why, that's how it works, right? The stronger the IMFs, the more likely you're gonna be a liquid or a solid. Okay, so in general now you can say, well, if shape wise, right? If I have a rod-like molecule, it's gonna have a higher boiling point than if I have like a ball-like molecule or lots of branching in my chain, right? So if I have a straight chain, it's gonna have a higher boiling point than a molecule with a lot of branches because that'll look more like a ball, right? Okay, so we got through our first IMF, right? Dispersion forces. Let's go to the board. We are going to make a table. First column, let's call it IMF. Second column, types of molecules that would exhibit that IMF. And third column, examples. So we just did dispersion, right? And what types of molecule has dispersion? Everybody, right? Everybody can have electrons and that are flying around in the molecule. That can be induced, that can have induced dipole. So all molecules. Okay. But we associate with nonpolar for dispersion because nonpolar has nothing else. Okay. Polar molecules not only have dispersion forces, but also has dipole, which is the next thing we're gonna go into. So it has multiple, and the dipole is stronger. Okay. But nonpolar, it only has dispersion. Okay. So that's why I connect nonpolar with dispersion forces. Okay. Even though technically it is in all molecules. Okay. So examples, we just said, CO2, right? C5H12 pentane that we just saw. Okay. Remember CO2, since it has two dipoles opposite each other, they cancel, so it's nonpolar. C5H12, you only have carbon-carbon and carbon-hydrogen bonds. Remember that CH bonds are considered nonpolar, right? Because it only has about 0.4 with that delta En. Remember that? Difference in electronegativity between carbon and hydrogen is only about 0.4. So we're like, it's pretty much nonpolar, okay? So C5H12, anything that's just carbon and hydrogen, is nonpolar. Hexane, right? Saw that. It's also nonpolar. Any gases at all? So if you just have argon, right? Any monatomic gases, you're gonna have it's gonna be nonpolar, right? Because it doesn't have anything for attraction. Okay. All right, let's look at dipole next. We are, remember, going in order of weakest to strongest. Okay, so strongest going down. So next one is dipole. Let's go back to our slides. Okay, so dipole are in polar molecules. Okay, because polar molecules have a delta plus end of the molecule and a delta minus end. We call that a dipole. So dipole happens between one dipole with another dipole. Okay, that's why it's called dipole. So two dipoles together. Okay, now they don't have to be the same, right? You can have dipole with two different molecules, right? But that's why it's called dipole. Right? So here's an example. This is acetone. Acetone is C. So this is a CH3. Then there's another C to a double bonded O, and then it's connected to another C with the 3 hydrogens. Okay, so 3 carbon with an oxygen, 6 hydrogens. This is acetone, and that's the fingernail polish remover. It smells, right? And if things smell, you know that it's more volatile. It has a lower boiling point because that's how it's getting over to your nose, right? It's going into the gas phase and coming over into your nose. So when you can smell something, most likely it's going to have a lower boiling point, and certainly acetone does. Okay. So acetone, though, has dipole forces. And how does that work? Well, remember, oxygen is more electronegative than carbon. So the oxygen end of acetone is delta negative, whereas the carbon and hydrogen end is delta positive. Okay. So now when this acetone sees a neighboring acetone, it's going to attract its neighbor in this way. The delta minus will attract the delta plus end of acetone. And so how are they stacked together in the liquid phase? Just like this. Now, if you have a third acetone coming in, it would be right here, right? So this delta minus will attract the delta plus, the other acetone. You can also see this in the EPM, called the electrostatic potential map. So in this map, you can see that the electron density is lying towards the oxygen. That's why it's red. And then the blue part is where it's deprived of electron density, right? So the red will go with the blue, right? So because the dipole is stronger than dispersion forces, a lot of the dipole um, compounds are going to be in the liquid state, right? The smaller ones will be in the gas state, but acetone, for example, is a liquid, right? So that's why acetone's a liquid. So what does that mean? Compounds that have dipole will tend to have a higher boiling point than those of dispersion forces. Comparing, if there's a similar molar mass, of course, right? So here's a good comparison. We have two different compounds with similar molar mass, formaldehyde and ethane. Both are around 30 grams per mole. So it's a fair comparison, right? And here's your structure. Formaldehyde has a C double bond O, okay? Now, C double bond O's are one of your most polar bonds, okay? So where's the delta minus? It's on the oxygen, and then delta plus is on the carbon and hydrogen. So you have a polar molecule, right? There's draw the bond polarity arrow. It's gonna face up, okay? So it's polar. Then ethane C2H6. Okay, it's just carbon-carbon and carbon-hydrogen bonds. So you don't even have to draw arrows. You just know that it's nonpolar, right? All CC and CH bonds are nonpolar. So ethane has dispersion forces. Formaldehyde has dipole-dipole. And so that's why formaldehyde has a much higher boiling point and melting point than ethane, right? Even though they are of similar molar mass. So, they have similar dispersion forces, right? Okay. Okay, here's a graph. We're comparing boiling points on the y-axis to the dipole moment, right? How polar molecules are. So the higher the dipole moment, remember, the more polar the molecule. So we're comparing from propane all the way to acetonitrile. Okay, you can see as we increase the dipole moment for each of these molecules, dimethyl ether, ethylene oxide, acetaldehyde, we are seeing an increase in boiling point. There. Why? Well, we have a stronger IMF, right? And so therefore, we need more energy to break that IMF for these molecules to go into the gas phase, right? Remember, when you go into the gas phase, you have to separate the molecules completely. That means you have to overcome the IMF that holds them together. You have to break it completely, right? So the higher the IMF, the stronger the IMF, the higher the boiling point is going to be. Okay, so there's some shortcuts for assessing polarity and then also assessing solubility because they go hand in hand. Okay, so when I looked at this structure here, okay, I didn't really need to draw arrows on top of it. I already could see that it was polar because I'm trained to see that, right? So there are certain shortcuts, certain groups that will make things polar and therefore water soluble. Okay. So remember the solubility rule is that like dissolves like. So things that are polar will dissolve in each other. And things that are non-polar will dissolve in each other. but a polar thing cannot dissolve in a non-polar thing and vice versa. Okay, so that's why the rule of thumb is like dissolves like. Okay, so these groups right here, they're called hydrophilic groups. Hydro stands for water. Phil means love, like Philadelphia, right? So water-loving groups, they are the OH groups. If you see CHO, you know that it's polar. C double bond O, just like in the acetone here, it's polar. COOH group, those are the acid, like carboxylic acid or acetic acid. Okay, that's gonna be polar. NH2, so also polar here, and then chlorine. Okay, and then the water-fearing groups, right, hydrophobe, right, are gonna be CH and CC bonds. We know because those are nonpolar. So nonpolar groups not gonna dissolve in water. These are the groups that are gonna dissolve in water. Okay, so then I can ask you, does pentane, which is C5H12, mix with water? Will they be miscible with each other? Will one dissolve in another? Well, it's pretty clear that that's not going to happen, right? Because C5H12 is nonpolar, and we know that water is polar, right? And so that's why they won't mix. Also, the same reason why oil doesn't mix with water, because oil is also a bunch of carbon-carbon and carbon-hydrogen bonds. Okay, so let's do this problem here. Which molecules have dipole-dipole forces? Okay, the three choices are CO2, CH2Cl2, and CH4. When you're faced with this question, guess what? Use what you know. Draw the 3D Lewis structure and figure out whether it's polar or not, right? This is, there's nothing new here. You guys already know how to do this, right? Now all you have to do is say what IMF it is, okay? So you already know how to draw the 3D. CO2, you would have seen that it's linear, so you need to draw it like this, okay? And now put the polarity arrows on top. You already know how to do this too. You're gonna point it towards oxygen for both. And then you're like, oh, they cancel each other out. It's not polar. So write the IMF. What is it? Dispersion. Okay, so not dipole-dipole. We were looking for dipole-dipole, right? Let's move on to the next one, CH2Cl2. That's four things bonded to carbon. It's gotta be tetrahedral, right? So I'm gonna draw my tetrahedral template. Okay, so CH, remember, I don't need to draw any bond polarity arrows on top of CH. I should do it for the Cl bonds. And it would point towards chlorine, right? Because chlorine is more electronegative than carbon. These arrows, they're both pointing this way, right? The net is that way, right? They're both pointing that way. So polar. And if it's polar, its IMF is dipole. Okay. Meaning, what does that mean? That means if I have another molecule, right? This be the delta negative end of CH2Cl2, and that'll be the delta positive end. So if there's another molecule of CH2Cl2, it would stack like this. Okay. The delta minus flow with the delta plus. Okay. So that's the dipole-dipole force, right? Is that dotted line. And that's what's holding these together. Does that make sense? And do you guys see why it's called dipole-dipole? This is a dipole, right? Because it's a polar molecule. This is another dipole. It's also a polar molecule. It just happens to be identical to that one, but they don't have to be the same, right? They could be different molecules. As long as they're both polar molecules, then it'll be a dipole attached to another dipole. CH4, you guys can see easily already. This is not dipole-dipole. Again, you have tetrahedral, right? So I can't even draw any polarity arrows on there. It's completely non-polar. So what is the IMF for this one? Dispersion. Okay. Pretty clear, right? Okay. Let's do these as well. CI4, CH3Cl. And HCl. Okay, CI4. That's tetrahedral again, right? Four things. Okay. So all arrows gonna point towards the I, as I is more electronegative than carbon. Okay, but it's all right. It's very symmetrical, and so all the arrows basically cancel. So you have no net dipole. You would conclude nonpolar as your molecule. And what's the IMF? Only present for nonpolar? Dispersion. Right? But that's not it. For CH3Cl, again, tetrahedral again, right? You don't draw any arrows for the CH because CH bonds are non-polar, but you do draw one for the CCl bond. Okay, there's nothing to cancel out that arrow. So you have a net dipole. This is a polar molecule. This is the molecule that has dipole. Okay. Okay. So that's how you would assess, right? That's basically how you assess IMFs. Start with the 3D, always 3D. That's why you guys have learned this already and have had lots of practice. And then you guys already know how to draw bond-polarity arrows and assign whether it's polar or not polar. The only new thing here is you assign now the IMF as well, right? Got HCl easy. Has to be polar. So IMF is dipole. Okay. So both C and B have dipole IMFs. Okay, so let's go back to the board and we can fill out now more of the table. Dipole, what types of molecule? Polar molecules will experience dipole. It's stronger than dispersion, right? Some examples we saw CH2Cl2 as an example, CH3Cl, HCl, right? A bunch of other things, okay? So, you know, again, just assess the polarity. If it's polar, it can be dipole. Now, the next one is called the hydrogen bond. Okay, H bond for short. The hydrogen bond I think of as a super duper dipole. So hydrogen bond is no different than a dipole. It's one and the same. It's just that it has a different name and it's put in a different class because hydrogen bonding is so much stronger than dipole, just normal dipole. So that's why I think of hydrogen bonding as super duper dipole. Okay, so let's take a look at what hydrogen bonding is. All right, so hydrogen bonding is going to occur in polar molecules where you have OH bonds, NH bonds, and FH bonds. Those three bonds, okay, are special. So why is that? Can you guys think of why why oxygen, nitrogen, and fluorine, why those are so special? Well, they're small and they're very electronegative. Those are amongst the most electronegative atoms on the periodic table. So that means that OH bond, NH bond, and FH bonds are very polar. That's why hydrogen bonding I think of as a super duper dipole dipole, IMF, right? It's it's just it's basically like a dipole dipole, but way stronger. The way to remember that, there's a little mnemonic device. Hydrogen bonding is fun. Okay. Hydrogen bonding is very fun, right? So HF, HO, and HN bonds. Okay. Okay. Um, so hydrogen bonding looks just like dipole dipole. Look at this picture. It's like dipole dipole. So one's a dipole, the other one's a dipole, right? You still have, the attraction between dipoles. Okay. It's just that now they contain OH bonds or FH bonds or NH bonds. And these bonds are so polar that the attraction is even stronger, right? So the IMF is even stronger. So water, that is your typical, your most basically iconic hydrogen bond, right? Is example is water. Okay. Why? Well, it's got two OH bonds, right? Not just one OH bond, it's got two OH bonds. So it can do hydrogen bonding in multiple directions. Okay. And this is also the reason why water is a liquid at room temperature, even though it's so small, 18.02 grams per mole. It should be a gas, but it's a liquid. And not only is it a liquid, it is a very high boiling liquid. It doesn't boil until 100 degrees Celsius. We know a lot of other liquids that are much bigger than water that boil at a way lower temperature. The reasoning, hydrogen bonding, right? Okay, other things that can hydrogen bond, ethanol as well. The stuff we like to drink at parties or maybe at home as well, or anytime, I guess. That we can, right? It's CH3, CH2OH. That's a 2-carbon chain and then an OH group at the end. So that OH bond, right, is going to do hydrogen bonding with the adjacent molecule. Um, and also that's why ethanol is, uh, you know, it's pretty high boiling liquid, but still not as high as water. Ethanol boils at around 78 degrees Celsius, but it has a way bigger molar mass, right? So if you compare it, what is this? 12 and 12, 24, 24 plus 16 for oxygen is 40, 45 with the hydrogens. Okay. So something like 45 grams per mole compared to 18 grams per mole. Yet water is the one that boils at 100 degrees Celsius and ethanol at 78. So why is that? Well, again, you can see water has two OH bonds, right? So it can do more hydrogen bonding than in ethanol. That's why ethanol boils at a much lower temperature, right? Both are liquids at room temperature. Okay, so how strong are hydrogen bonds? Well, it is the strongest IMF that we know. But even if, even compared to covalent bonds, it's only 2 to 5% the strength of covalent bonds. So how strong are covalent bonds? The intramolecular bonds that hold the molecules together, are very, very strong, right? But the bonds that hold the molecules to each other, 2 to 5% for the hydrogen bond. Okay, so some comparisons. We are now comparing ethanol and dimethyl ether. Both have a molar mass of 46.07 grams per mole, so fair in their dispersion forces, right? Now, why do they have such a large boiling point? Their dispersion forces are pretty much the same. Well, it's because ethanol has hydrogen bonding and dimethyl ether has dipole-dipole. You guys see that? Okay. Let me draw it so that you can see it better. So the space filling is a little hard to see. Okay, but let's draw the Lewis structure, 3D. So we got ethanol, right? CH3, CH2, O H. I'm trying to draw, a bigger molecule in 3D. Right? I could have drawn this out in 3D too, but it really doesn't help with our assessment. Doesn't really help with our assessment because all we care about is what's going on here, right? We have OH here, so automatically we can say hydrogen bonding. It is bent, so it's definitely polar. Right? You can put the arrows like that, okay, towards oxygen, right? So it's definitely polar with an OH bond. So IMF is hydrogen bonding. Then when we look at dimethyl ether is just CH3 O CH3. So again, I can draw it in 3D, right? Right here is bent. Okay. So I can draw my dipole arrows like that. Again, I see that net is up, right? Both arrows are pointing in an upward direction. So we say this is polar, but the IMF is just a regular dipole because it does not have what? OH bonds, NH bond, or FH bonds. Okay. So just dipole. Okay, so that's why this one has a boiling point of, let's go back here. Ethanol has boiling point of 78.3 degrees Celsius, whereas dimethyl ether is not even a liquid at room temperature. It's a gas, right? Crazy, because they have the same molar mass. So how much of a difference does hydrogen bonding make, right? This is a liquid now, right? And this is a gas. And you can look at the melting point, see, right? Same trend, way higher melting point for ethanol versus dimethyl ether. Yeah. Now let's look at this graph, right? What are we comparing here? Hydrogen compounds of group 4A and group 6A. Okay, so let's look at group 6A first, which is the purple line. Boiling points on the y-axis, right? Molar mass is on the x-axis. We can see that as molar mass increases, dispersion would increase, right? Can we verify that CH4, SiH4, GeH4, and SnH4 are all nonpolar? Because they're all tetrahedral, right? So all nonpolar, meaning all dispersion forces. And we know how dispersion forces work. The higher the molar mass, the stronger the dispersion forces, and the higher the boiling point. No surprise, right? No surprise in group 6A. But what the heck's going on in group 4A? I look at the screen. H2S, H2SE, and H2TE. Oh, it has the same trend, right? Because again, as you go up in molar mass, you're gonna have an increasing boiling point. But water being of the lowest, the lightest, right? The lowest molar mass is way up here. It bucks the trend vastly, right? Vastly bucks the trend. You got 100 degrees Celsius boiling point for water due to what? What is its IMF? Hydrogen bonding, right? H2S does not have hydrogen bonding. It's a dipole, right? And then H2SE and H2TE, smaller, right? Is dipole as well, but it's bigger. Okay. So it does have a higher boiling point than say H2S. But none of these have hydrogen bonding, right? It's only H2O because it has the OH bond. Okay, let's look at this one. One of these compounds is a liquid at room temperature. Which one and why? All right. Go to the board on this. So A, we have formaldehyde, and I'm going to redraw formaldehyde too. So the way that they have the Lewis structure, notice that they're not doing it in 3D for you, right? So you got to be careful there. You have to do it in 3D yourself, okay? So you can tell it has 3 electron groups around the carbon, which should be trigonoplanar, but they didn't draw it as trigonoplanar. So we need to redraw it as trigonoplanar. Formaldehyde, right? Then the middle, fluoromethane, as you can see, has 4 electron groups around it, but it's drawing it as a cross. You got to redraw that as well. Okay, so don't let the problem trick you. You know that you need a 3D structure. Oh, CH3F. Okay, that one is called fluoromethane. And then the third one is hydrogen peroxide. Again, I did not draw this to the correct geometry. In fact, they don't even put the lone pairs for you in there. Very tricky, right? So watch out for that. Check all these structures. When if you have H2O2, you need 6, 6, 12, 14 valence electrons. They're only showing you 6, right? So where's the other 6? 2 lone pairs on each oxygen. So if I have 2 lone pairs on each oxygen, that's a tetrahedral, right? Tetrahedral bent on the oxygens. Okay, so I need to redraw that. Like this. Okay. So careful with these problems, all right? Always check to see that you have the best structure. Don't just trust what they give to you, okay? So, right? They didn't even put the lone pairs in there for you. So bent here, and again bent. Okay. Now we can put polarity arrows on top because all of these are in 3D, okay? So this is polar, right? We don't need bonds, or I mean, arrows for CH bonds. So IMF here is dipole, dipole. In this structure, don't draw any for CH, draw for CF. So it is polar as well. And IMF is dipole, dipole. Okay. And then in this last one, quite easy to see, right, that you have OH bonds. I mean, you don't even need to draw arrows anymore. As long as you see OH bonds, it's going to be hydrogen bonding. Okay. So the question asks, which one of these is most likely to be a liquid at room temperature? Well, which one has the strongest IMF? This. So we know that hydrogen peroxide is a liquid. Both of these are gases. Formaldehyde and fluoromethane are both gases at room temperature, right? Because they have dipole-dipole, but their molar mass is a little small, right? Okay, so you guys see how that works, right? Pretty cool. We get to take our knowledge now and apply it, right? This is application of all of the theory that you guys have been learning, right? All the bonding theories and things like that. Now you see why it's useful, right? Why we learn those theories. Okay, so let's continue with our table. Just learned about hydrogen bonding in what types of molecules? Also polar, right? Molecules with HF, HO, and HN bonds. Okay. Hydrogen bonding is super fun, right? FON. So examples, water, NH3, methanol, you saw that, CH3CH2OH, okay, etc. Okay. HF also has hydrogen bonding, obviously. Okay. All right, so our next one that's stronger than the H bond is called dipole, ion dipole. Okay. So let's see what that is. Like it sounds, it's going to be between an ion. Right? An ion is something that's completely charged, like negative or positive, and polar molecule, right? A dipole. So let's look at examples of that. Here we go. The situation of salt water is ion dipole. Salt water, remember table salt is Na plus and Cl minus. When you drop it into water, water comes in between, separates the Na plus and the Cl minus, destroys the crystal lattice, and then the water molecules surround each ion. The delta plus end of water will surround the chloride, right? Since it's negatively charged. And then the delta minus, the oxygen end of water, will surround the sodium plus, right? And they're keeping them from being together. And so that's why you don't see solid anymore, solid salt anymore. But you know it's still there because if you drink it, it tastes salty, right? So it's dissolved. That's what we mean when we say that salt is dissolved in water. And this solvation of the ions is an ion dipole force because what's holding, right? What is the attraction between the chloride and the water molecules is between an ion, right? A fully charged Cl minus and a polar molecule, which is water. You see that? This is the ion and this is the dipole. So, and the force that connects them is called the ion dipole force. Okay? Very literal, right? So it's easy to remember. So again, it's always between an ion and a polar molecule. Here's the other one. Our sodium plus is the ion and water is a polar molecule. So all of these dotted lines, all of these IMFs are called ion dipole forces. Okay. All right, so let's complete our table. Examples would be NaCl aqueous. So look for that. Anything that if you see an ionic compound with aqueous next to it, it has ion dipole forces. Okay, so anything, right? It could also be calcium, bromide, CaBr2 aqueous. Okay, oh, that's ion dipole, right? Because that's the dipole is the water, and then these are ions. Other things too, right? Could be magnesium, iodide, aqueous. Okay. Lots of examples. Okay. But that'll be, technically, yeah, that's the strongest, your strongest IMF there. Okay, so in summary, guys, right, dispersion forces are the weakest. They're present in all molecules. The strength of the dispersion forces have to do with their molar mass. Increasing the molar mass increases the dispersion forces and therefore increases the boiling point. Right? Polar molecules are the ones that have dipole-dipole forces. And then hydrogen bonds are just a super duper dipole-dipole because they have HF bond or HN or OH bonds in there. Okay. And then you got your ion dipole as the strongest IMF. It's between a charged particle and right an ion and a polar molecule. Let's put some numbers to it. So this table has the IMFs also from weakest to strongest. And now we can see the strength, right? In kilojoules per mole. Dispersion, small, right? Weakest. So only about 0.05 to 20 kilojoules per mole. The 20 kilojoules per mole are for the really large nonpolar molecules, right? And that strength comes from all the dispersion forces kind of adding up over a long distance, okay? Dipole, you're going to see the low end is 3 kilojoules per mole, okay? So much higher than the low end of dispersion, right? Hydrogen bonding, now you can see why it's in its own class. 10 to 40 kilojoules per mole. That's compared to the dipole, regular dipole, right? 3 to 20. And then your ion dipole is even stronger than that. Why? Because you actually have a charge, right? You don't just have a dipole, you have an actual charge and a dipole. And so it's 30 to about 100 plus kilojoules per mole. All right, guys. So that's it for today's lecture. I'm going to see you guys back for lecture 2.